Naimbagnal Dao, architects and civil engineers of the future. Welcome to the Eiffel Tower. I mean, welcome to your online class in strength of materials or mechanics of deformable bodies. I am your instructor, Daryl G. Emblebeen. In this video, I will discuss bending stress example 1. The simply supported beam in figure A has a rectangular cross-section 120 mm wide and 200 mm high. Letter A. Compute the maximum bending stress in the beam. B. Sketch the bending stress distribution over the cross-section in which the maximum bending stress occurs. C. Compute the bending stress at a point on section B that is 25 mm below the top of the beam. Before we can compute the maximum bending stress in the beam, we must find the maximum bending moment. Before we can find the maximum bending moment, we must sketch the moment diagram. Before we can sketch the moment diagram, we must sketch the shear diagram. And before we can sketch the shear diagram, we must determine the support reactions. Did you follow? Simply put, we must first determine the support reactions. And in this problem, we must first determine the reactions at support A and support E. The beam is under a uniform load of 6 kilonewtons per meter all over its length, and also under a concentrated load of 15 kilonewtons at point D. So first, we determine RE. We assume it to be acting upwards. And later, we check whether our assumption is correct or not. We can solve for RE by summation moment at E equal to 0. So first, RA tends to rotate clockwise about point E. So positive. It has a perpendicular distance of 3 meters from point A. Next, we have the uniform load of 6 kilonewtons per meter. We multiply that to the overall length of 3 meters. So this is the resultant force, 6 times 3. Let's try to sketch that in the beam. The resultant force of a uniform load is acting at the midpoint of the uniform load. So that means that from point E and from point A, it is 1.5 meters. We multiply the resultant force 6 times 3 times the perpendicular distance of the resultant force from point E, which is 1.5. And it tends to rotate counterclockwise, hence negative. And for the concentrated load of 15 kilonewtons, it also tends to rotate counterclockwise about point E, hence negative. And its perpendicular distance from point E is 1 meter. After taking into consideration all the forces and their perpendicular distances, we equate them to 0. So that we can calculate for RE, which is equal to positive 14 kilonewtons. The positive value means that our assumption that RA's upwards is indeed correct. Next, we solve for RE. Again, we assume it to be upwards. We can solve for RE by summation moment at A equal to 0. For RE, it tends to rotate counterclockwise about point A, hence negative. Its perpendicular distance from point A is 3 meters. And again, for the rectangular or uniform load, that is 6 kilonewtons per per meter times 3 meters. This is the resultant force. And it tends to rotate clockwise about point A, hence positive. And its distance from point A is 1.5 meters. And for the concentrated load of 15 kilonewtons, it tends to rotate clockwise about point A, hence positive, and its perpendicular distance from point A is 2 meters. We can now equate everything to 0, and we can calculate RE equal to 19 kilonewtons. Again, the positive value means that our assumption that RE is upwards is indeed correct. After solving for RE and RE, we can actually countercheck whether our support reactions are correct. How? Simple. By having summation Fy, or summation of vertical forces, equal to 0. If our summation Fy is equal to 0, that means that our support reactions that we computed are correct. So I want you to work on summation Fy equal to 0 and comment down below if it is indeed equal to 0. Okay. After solving for the support reactions, we're now ready to sketch the shear and moment diagrams. In this problem, I'll be using the area method. First, we sketch the shear diagram. At point A, we have a positive or an upward support reaction equal to 14 kilonewtons. So it means that we go up 14 kilonewtons. Going from point A towards point D, we have a downward uniform load of 6 kilonewtons per meter over a distance of 2 meters. So it means that we add 14 plus negative 6 times 2. That is equal to positive 2. How do we connect positive 14 and positive 2? We connect them simply with a straight line. And at point D, we have a concentrated downward load of 15 kilonewtons. So we add 2 plus negative 15, and that is equal to negative 13. We go down from 2 to negative 13. And going from point D towards point E, we have a downward uniform load of 6 kilonewtons per meter over a distance of 1 meter. It means that from negative 13, we add negative 6 times 1. So negative 13 plus negative 6 times 1 is negative 19. Again, how do we connect negative 13 and negative 19? We simply connect them with a straight line. And at point E, we have an upward support reaction of 19 kilonewtons. It means that we add negative 19 plus positive 19, and that is equal to 0. Therefore, our shear diagram is correct because we went from 0 to 0. Next, we sketch the moment diagram. At point A, we have no couple, so we begin with 0. And from point A towards point D, we compute the area of this trapezoid with a base 1 of 14 and a base 2 of 2. Recall the area of a trapezoid that is equal to 1/2 times the quantity of B1, base 1 plus base 2 times the height. So if we compute that, we have 1/2 times base 1 is 14 and our base 2 is 2 times the height, which is 2. That is equal to positive 16. So from 0, we have positive 16. Our problem is how do we connect 0 and 16? At point A, we have a positive. You have to recall that if the graph is linear in the shear diagram, it becomes a second degree curve or a parabolic curve in the moment diagram. So this means that this linear graph will become a parabolic curve in the moment diagram. So we know now that this will be a parabolic curve. But another problem is, does the parabolic curve concave upward or downward? So at point A, the parabolic curve should have a positive slope. And at point B, the parabolic curve should have a zero slope. For that to be possible, the parabolic curve should concave downward. So from 0 to positive 16, the parabolic curve concaves downward. And from positive 16, or from point D, we compute this, again, a trapezoidal area. And in this case, has a negative value. So we have base 1, 13, base 2, 19. So 1/2 times base 1 is 13, plus base 2 is 19, times the height, which is 1 meter. That is equal to negative 16. So we add 16 plus negative 16, that is equal to 0. Again, this linear curve in shear becomes a parabolic curve in moment diagram. But does it concave upward or downward? Again, at point D, the parabolic curve should have a zero slope. And at point E, the parabolic curve should have a negative slope. And for that to be possible, this parabolic curve should concave downward. Again, we went back to 0. That means that our moment diagram is correct. We went from 0 to 0. Okay. After sketching the shear and moment diagrams, we can now determine the maximum bending stress, which is equal to 16 kilonewton meter, occurring at point D. Next, we solve for the moment of inertia of the cross-sectional area about the neutral axis. We have a rectangular cross-section with a width of 120 millimeters and height of 200 millimeters. Since this is a symmetric cross-section, the neutral axis is the axis of symmetry, or the neutral axis coincides with the centroid of the rectangle, as shown in the figure. So for rectangle, I is equal to bh cubed over 12, wherein our b in meters is 0.12 and our height in meters is 0.2. Calculating, we have I equal to 8 times 10 raised to negative 5 meters to the 4th power. Next, we are now ready to solve for the maximum bending stress in the beam, given by this formula, where M max is the maximum bending stress equal to 16 kilonewton meters, and the C is the distance from the neutral axis to the top or bottom of the beam, which in this case is both equal to 100 millimeters. And our I, we just solve it. So substituting, now we have to be consistent with our units. Our moment should be expressed in Newton meters. That's why we have 16 times 10 raised to 3. And our C should be expressed in meters, so we have 0.1. And our I should be expressed in meters to the fourth power. So we don't need changing for I. Solving, our unit will be in Newton per square meters or pascals. That is equal to 20 times 10 raised to 6, which is equal to 20 megapascals. Therefore, the maximum bending stress in the beam is 20 megapascals. For letter B, we need to sketch the bending stress distribution over the cross-section on which the maximum bending stress occurs. The maximum bending stress occurs in the cross-section of the beam that carries the largest or maximum bending moment. And in this problem, that is located at point D. So for the bending stress distribution, from the neutral axis towards the top of the beam, and from the neutral axis towards the bottom of the beam, the bending stress varies linearly. Our maximum bending moment is positive 16 kilonewton meter. And for a positive bending moment, we recall that the beam smiles. So that the top of the beam is under compression and the bottom of the beam is under tension. So that at the top of the beam we have a compressive stress of 20 megapascals, and at the bottom of the beam we have a tensile stress of 20 megapascals. Notice also that the compressive and tensile stresses are equal in magnitude. Why? Because we have a symmetric cross-section, wherein our C is both equal to 100 millimeters. And you might ask why we have a zero bending stress at the neutral axis. Why? Because our C at the neutral axis is simply 0, which results to a 0 bending stress. Okay? For letter C, we need to compute the bending stress at a point on section B that is 25 millimeters below the top of the beam. Before we could compute the bending stress at point B, we need to get the bending moment at point B. So let's do just that. First, we need to get the shear at point B. In the shear diagram, first we go up with 14 kilonewtons. And from point A towards point B, we have a downward uniform load of 6 kilonewton per meter over a distance of 0.8 meter. So what we do is, we add 14 and negative 6 times 0.8. That is equal to what? That is equal to positive 9.2. So that is the shear at point B, positive 9.2. Now we can proceed with the moment at point B. So again, we begin with 0. And to get the bending moment at point B, we simply get the area of this trapezoid. Base 1 is 14, base 2 is 9.2, and the height is 0.8. Recalling that the formula for the area of a trapezoid is 1/2 times quantity base 1 plus base 2 times height. So from 0, we go 9.28 kilonewton meter. So 9.28 kilonewton meter is the bending moment at point B. So the bending moment at point B is equal to positive 9.28 kilonewton meter. Next, we determine our Y. So the point of consideration is 25 millimeters below the top of the beam. So this is 25 millimeters. And the Y we're referring to is the distance from the neutral axis to that point. So this is Y. And to compute for Y, we simply subtract 125. Because again, Y is the distance from the neutral axis to the point of consideration. So we have 100 minus 25 is equal to 75 millimeters. And in meters, that is equal to 0.075 meters. Now we're ready to solve for the bending stress, given by the formula negative my all over I, where m is the bending moment, y is the distance from the neutral axis to the point of consideration, and I is the moment of inertia of the cross-sectional area about the neutral axis. So we substitute our values. Our m should be in terms of Newton meters. That's why we have 9.28 times 10 raised to 3. Our y is 0.075 meters. And our I, as previously solved in terms of meters to the fourth power, is 8 times 10 raised to negative 5. Calculating, the bending stress is equal to negative 8.7 times 10 raised to the sixth power pascals. And in terms of megapascals, that is equal to negative 8.7 megapascals. So the negative sign indicates compressive stress, which is true. Why? Because if we have a positive moment, the top of the beam is under compression, while the bottom is under tension. So we have a compressive bending stress at a point on section B that is 25 millimeters below the top of the beam.